Right, so welcome to my session. I appreciate all waking up so early after the long boat trip yesterday. I'm responsible for the software architecture at Mellanox. Been working there for the past 14 years, so I've been doing lot of hardware and software throughout my lifetime there. So I'm going to talk about the futures of the interconnect, and probably going to talk about things that we're doing and in light of them, try to see how the future will look like and the challenges that we're facing. So looking a little bit into the crystal ball, I wanted to talk a little bit about the high-level challenges that we're facing around the HPC, the problems that we would like to solve and improve as we move toward the exascale computing. So I just listed a couple of things, very high-level challenges that we're going to face both in the pretty much at all level of the stack. It can be in software, APIs, hardware, and all of that. And I think a good solution that will lead us to exascale will solve all those points throughout the different components. So definitely we're talking about very massive computing element count. We're talking about tens of millions of functional units that can be processed as threads or anything that can compute, and that's going to also evolve over time. And for that we really must make sure that our communication are good, they're scalable for both point-to-point and collectives, because the pressure to connect all those nodes efficiently is going to become more and more critical. And that stands for both point-to-point and collectives, especially at large scales. So the next thing that happens is that there are consolidation of units. So there are more and more cores in CPUs and in GPUs. So a single networking point, the pressure now is becoming more and more on the scalability of the HCA of the network communication to be able to handle those many unit count and to work efficiently with all the concurrency, both of the local operations that are needed as well as the remote operations. And that number continues to grow, especially if you're sharing an adapter between multiple GPUs and multiple cores that are on the node, and their number keeps increasing. Memory hierarchy is another story. Compute become more and more dependent on memory hierarchy, caching, and all of that, and that that becomes at all levels. Can be CPU caching, can be CPU memories, NUMA nodes, and can also be storage hierarchy. So all of them really require attention, both at application awareness and in network access to be able to better utilize them. There have been multiple talks about that in all areas, so this is a big challenge, and in particular in communication, being able to move data between storage tiers, for example, as well as when we move data, how fast can we bring that data into the CPU cache in order to make it efficient. Other thing is, the amount of memory per functional unit seems to be decreasing. So we're talking about very small memory chunks that are out there per functional unit. So you'll need to be able to move very efficiently memory between functional units. So for that, you definitely need very low latency for being optimal, as well as high bandwidth for moving larger chunks of data. Functional units are heterogeneous. There is like the accelerators, there are the CPU. You need to accommodate for that by supporting the different patterns and accessibility options for the different data. Failures is going to be more and more part of our life, and each job is going to have more and more failures all the time, so we need to be able to deal with this. It could be dealt with resiliency, it could be dealt with redundant, and also protecting the data. We'll touch this a little bit later, but definitely networking can be also one point of failure itself. It has many components, and this has to be addressed, and it can also help mirror stuff and actually bring more resiliency by the right algorithms. And last thing is that data movement is becoming very expensive, and this has to be optimized. We talked about that, how painful it is to move data. So we need to make sure we optimize on data movement. If we need to convert data types, things like that, those could also be offloaded in order to avoid data copies and data translations within the CPU. A little bit more about, the HPC interfaces, the MPI and the SHMEM. We need to put a lot of focus on the synchronous operations, and that's, at both places, both in, the applications, making them work with the synchronous because it's more complicated to develop this way, and also have more and more efficiency in the actual implementation of the asynchronous operations. So add them to the API, add them to the software, add them to the communication library and the hardware. Make things maybe even topology aware. I don't know, even maybe to the application or below that. Avoid as much as possible system noise issue. So as much as possible, try to avoid the bad impact of this, because this completely slow down large jobs. And last thing is, to minimize on the data motion. Try to avoid as much as possible data movement that is not necessarily data copy, data translation within the CPU and so on. So try to use a single path on the data, especially when you're trying to move something from one place to another. Do it as much as efficient as possible. So I'll start, with the first thing that comes, at least to my mind, when I'm talking about interconnect. I think the standardization of the interconnect is something that is a very important piece of choosing the right interconnect. Pretty much, if you look at InfiniBand, it has been a standard for years, and I think standardization enables interoperability, mix and matches of different components, and regardless of number of vendors and things like that, you can look at an ecosystem that could be built. The wire protocol has influence of all the people that care about this, and as much as we could do it standardized, maybe standard with vendor extension, that's also very valid, but at least you have a common denominator that enables you to build correctly a heterogeneous system that has mix and match of vertical and horizontal components, so that can bring together community things and develop an ecosystem together to succeed. Another thing that is very important is working in open source and having extensible interfaces. That also enables a very good ecosystem. So you could usually take your application and extend them. You have different set of APIs, and you can actually grow. And as high-level thoughts about our communication stack. So basically, we want to have verbs that keep evolving over time. So the verbs will have more and more functionality that we're going to add them as part of the extended verbs. Some hardware will have them, some hardware will not. So you'll be able to take advantage of the best of the services, but still keep the same good old API that tons of applications have been written for them. And basically on top of that, and there are going to be many protocols and accelerators and interfaces that will be optimized for different tasks. For sockets with different level of offloads, for RPC, packet processing, storage, and so on. And especially, the APIs that we're using for high-performance computing, they could be further tuned according to extended verbs and specific vendor extensions according to the feature set that the actual hardware can offer, and that could give the best optimization. And once you have those interfaces, it should be trivial to map them to hardware operation. It can be very lightweight. And if something lightweight is missing, then it's quite straightforward to add it as part of the verbs extensions. So after I finish the standard stuff, I want to talk about the three S's that are very important in interconnect, which are speed, speed, and speed. So I think that's the number one that comes in mind for the evolution of the interconnect, and it's it's getting more and more complicated to keep up with speed, but this is a very important thing. And when I'm talking about speed, then definitely I'm talking about characteristics of bandwidth, of latency, and message rate. Each one has its own influence about the various things. And as we move forward into 100 gig EDR and beyond that EDR, it's become more and more challenging to deliver. And this is why we keep looking at new technologies that will enable going forward to 100 gig and beyond. Definitely, if you're looking at exascale computing, we're going to evolve through 100 gig and 200 gig and maybe even manage to squeeze in the generation following the 200 gig to reach exascale computing in 2020. So, I mean, today we're at 56 gig, so that's the dominant dominant speed, and over 2014 and 2015, we're going to see entrance of EDR speed, and few years after is the 200 gig. As I mentioned, these are going to be very challenging, but they're going to be speeds that are essential to keep up with the computation. With the computation needs and scaling. So you can see in today's latest infinite band adapters that the architecture is actually even ready for 100 gig. So you could get 100 gig out of the node by using the two rails, the two ports of the HCA, and you can actually get almost two ports of 56 gig. At saturation to deliver 100 gig coming out and in to the node, as well as very high message rate of over 130 million messages per second. This graph pretty much illustrates the importance of being able to scale with the message rate, and similarly you can see the scaling needed in bandwidth. Actually, I brought here a spec int, but you might be more wanting to look into a spec floating point. But anyway, this graph shows, the gray bars show the improvements in spec int processing capabilities of the CPUs throughout the years, while the blue bars are showing actual VPI or the latest InfiniBand speeds of going up to 56, and later on we're going to double that into 100 gig and so on. So unless you scale with the interconnect and being able to pump higher message rate, then your compute become inefficient. And those are the things that are really matter. And in fact, our target for exascale is to always be able to match the I/O bandwidth that is available in the CPU to make it available for point-to-point communication between the different compute nodes. Another graph showing the performance, the bandwidth of over 2 generations of ConnectX-2, ConnectX-3, and the current generation. So you can see the bandwidth depending on the message, the bandwidth of unidirectional and bidirectional, and the left graph showing the evolution of ConnectX-2 from PCI Express Gen 2 to ConnectX-3 to PCI Express Gen 3. And then the two upper graphs are ConnectIB with the two Intel CPU generations. You can see also the slightly more improvement in the new platform. But basically, what you see here is that all the bandwidth that is available on the I/O can go out and in through the adapter, and that's the number one for being able to scale. And we actually are seeing applications that can benefit throughout high-performance computing and as well as storage. Here you can similarly see the same behavior in bidirectional, and you can see actually the higher gap that Ivy Bridges managed to drive with bidirectional bandwidth. All right, so another S is scalability, and this is definitely something that is very important. And actually, each time we think we find another thing that we want to make more scalable. So I guess in order to get to exascale, we need to improve every single component that should be scalable. And I'm going to give you a few examples of things that we've been doing, we're working on, and things that are more futuristic. But the list is long, and I'm trying to just give the high-level overview for how to scale. So first of all, I'm talking about collective operations, which I mentioned is really important, and you need to make them as efficient as possible. So you can look at topology aware. You can take advantage of hardware multicast and use that as most efficient as possible. You can try to run collectives on a different virtual fabric using different virtual lane to make sure that the data moves fast and more efficient. And you can use more and more offloads. The graphs here are showing reduction in barrier, performance optimization, up to 2,000 processes that we're running, and basically, the scalability of our fabric collective acceleration really gets you to really nice scalable numbers in terms of latency for the operation. And we need to keep evolving that in order to scale more and more efficiently with collectives. So the next evolution that I'm going to talk about deals with the transport itself. So we started with a very naive approach of doing a point-to-point communication that every process will end up talking. And this is just illustration. In practice, there are way more lines even in this small, very tiny small cluster. So this is really just a high-level illustration. But basically, if each node wants to communicate with each node and each process in each node want to communicate, and those numbers really grow up exponentially. So running reliable connection has scalability problem in many sense, especially for those high performance computing, because it takes a requirement to pin down a lot of memory for the sake of computation, for the sake of the communication. It also has bad utilization of the caches in the hardware and so on. So actually, when you try to analyze what's happening over time, is that not all the cluster is active, and basically there are more connections that are working, and most of them just don't work at the same time. And you could actually optimize the hardware, the communication hardware, to fit the actual demand for communication, and rather than statically allocating all of them. So basically, we came up with an approach called dynamically connected transport mode, where we could, where we made the connection establishment a very lightweight operation. So basically, you need to have an endpoint per process, and that endpoint can communicate with the rest of the world. But as opposed to unreliable datagram, dynamically connected offers reliability with all the acknowledgements and message tracking. It can support very large messages, same thing like RC, reliable connection. And also it supports the RDMA and atomic operation. So basically with dynamically connected, we solve both the memory consumption. In this graph, you can see the demand for memory pinned down just for communication. So you can see, with reliable connected, if the cluster is small or going to 100K nodes, then this thing exponentially grows, and this was definitely not an option. And then we added shared receive queue, which again pushed down the numbers, but the numbers still are big and they're exponential. And then we added the XRC, which still has a growing demand for memory as cluster size grows. It's still significantly order of magnitude less, but still it needs way more memory. And then we came up with a dynamically connected, which stays flat and actually normalizes the amount of memory that needs to be pinned down for communication only according to the actual demand and actual concurrency of the cluster. And here we can see some preliminary numbers for dynamically connected. Those are improvements for all reduce and for all-to-all in percentage, depending on message size. And we'll see more and more things coming up on dynamically connected transport service. We believe that this is the right way to go for communication in a very large-scale multi-connection environment and significantly reduce the toll you pay on communication. So another item that we saw that required our attention to make more scalable is the Subnet Administrator. I don't know how many of you are familiar with the Subnet Administrator, but basically in the InfiniBand architecture, there is a centralized place where of the Subnet Manager and the Subnet Administrator that enumerates all the fabric, discovers it, derives some kind of a topology, understanding of the network, and then calculates the different routes between the different nodes. And what we saw is that actually the number of routes grows in n square. So the more nodes you have, it's significantly impacting the growth of the number of routes that needs to be calculated. And when a cluster starts, then basically there is a subnet manager that's doing some kind of a DFS enumeration of the network, and we took some high number. It's going to be very small in a few years, but for today is relatively big number of 40,000 nodes. And we tried to do our calculation of what does it take to scale it. So basically the subnet manager, retrieving the topology file and all of that and enumerating the network, that's something that could still be handled. But we end up with having about 1.6 billion path records, which is the n square of all the nodes that need to communicate with all the nodes. So given that, the subnet administrator will need to respond with those 1.6 billion path records. It will need to calculate them. It will need to respond with them. So calculation only takes 1.5 hours. And responding them, assuming some rate of a single host, rate of 50K queries per second, it's going to take 9 hours. So this is completely unacceptable. So what we came up is an approach that takes this n square problem and make it just linear back just with a number of nodes. So basically, we took all those 1.6 billion path records and we divided them into a number of nodes that will process those queries. So we kind of distributed that work of calculating the path and responding to the path queries. And once this is distributed, so it can be distributed theoretically to all the nodes, but we took an approach that it will, distribute it to 1/100 or 1/200 of the nodes. So this problem became a distributed, scalable SA, and each one of the nodes that is the access layer that is servicing path query will only need to deal with paths that are relative to the host that access it to ask for path records. So basically, we took this 1.5 hour calculation and 9 hours to serve into something completely distributed that at best case, we're talking about 40K or 8 million path records that will be handled by a node. So I think that, this project is evolving and there's way more here. But I think it covers all the SA scalability, and with that we could enable better scalability here of this component, and we can deliver quality of service. And I think it's the right approach here, and we'll solve all the potential issues with them using this new architecture for scalable SA. And there are more things on scalability, and I just want to highlight a few of them, but the list is, as I mentioned, long, and as we evolve, we'll find more and more things we want to do on terms of scaling. So first of all is, supporting the different topologies. So I know that, from InfiniBand standpoint, the dominant topology today is fat tree. People build it non-blocking, blocking, whatever flavor they want. This is the dominant one. It's very efficient when you don't anticipate the different traffic patterns. It has good resiliency for switch failures in the cores and so on. So basically, this one is fairly adapted. But We do see requests from partners and customers to use and to support other topologies. And basically, those topologies require implementation of different routing algorithms in the subnet manager. So hardware itself has no issue to support those different topologies. It's basically about enabling new routing algorithms. So mesh and 3D torus are already supported, and Dragonfly is going to be there. So basically, we'll give the flexibility of choosing whichever topology that is interesting for the deployment. We can support any one of these. InfiniBand routers. So this is something that makes a lot of sense when you want to scale the InfiniBand network. Basically, today you can build clusters. They can be fairly big. They can be tens of thousands of nodes. However, there are so many reasons why people would like to use InfiniBand routers. And still, with the routers, you can get all the RDMA goodies, and you can move from one cluster to another and get very good performance. It's like adding yet another hop in a factory topology. But this brings some more isolation. So for example, you can run separate subnet manager in each one of the clusters. So if there is a big failure or a maintenance or anything like that, it will only have impact on part of the cluster. It will not have impact on the rest of the pods that are in here. It could enable, better resiliency and connectivity between different buildings and so on. And it can also enable to connect legacy clusters, maybe storage cluster, production clusters, experimental cluster. All of them can be connected with the routers, and still you have the different administrative domains. So each cluster is a standalone on its own and can have no impact on stability of the other clusters. Another item that is interesting, actually this one is out there for a long while, and I see there's a growing interest for QoS. I think few use cases can be used for collective operations and using storage and networking on the same cluster. So there is a lot of room for doing QoS, and we can see that growing interest, and this technology is pretty much out there and can be used for deployment. And last topic I wanted to bring here is about the distance. So we have technologies that can go beyond few meters in the data center. So you can scale your cluster between floors, between buildings, and even campus-wise. Could be building one cluster that can grow beyond a single room. Or could be technologies to connect different legacy clusters in different locations. So with those technologies, you'll be able to scale. And again, about scalability, there are so many other topics, and we'll see more and more things that are evolving, because in order to get to exascale, we need to take every single component and improve that over time. Network offload. So, in Mellanox for many years, we're pushing the approach that CPUs and all the compute elements should focus on doing the computation, and anything that has to do with the networking will be done by the adapter. So this means a lot of offloads. And actually, the things start to blend because there are many applications that you could do. You could offload things while data is being moved. You could do some calculation on the data. You can focus also on things and operations that you can actually do on the network or on the adapter, on the switches, and they're going to offload, and basically offer better overlap between communication and computation. So a few examples. So, CoreDirect is one of the technologies we have to offload collective operations. And basically the concept in CoreDirect is that similarly to the way you write a computer program, you can write a network program. So basically you can go to the network adapter and give it a list of operations to be done. Operations could be, send a message or receive a message, enable some operation, do some kind of a calculation, and then once you push down this list of tasks, this network program into the adapter can process those things one after the other with all the interdependency and synchronization that is being pushed into the hardware. So basically, there is a high-level illustration of a task set that could be pushed into multiple queue pairs of the hardware to process those elements. Basically, the core direction can be very useful for, doing collective communication, doing everything asynchronously, and that really offloads the CPU, because the CPU doesn't need to rely on a progress engine. Everything can be pushed ahead in advance to the hardware, and beyond that, it can have better, overlapping of communication and computation, and that's also make sure that the progress is being processed by the hardware itself. And definitely avoiding system noise, whereas system noise will have zero impact on the HCA behavior. And this technology, aside, from the high level, so we keep adding more and more primitives and more offloads that will be needed in order to implement different algorithms for collectives and different computation as needed by the evolving APIs. Another topic, we talked a little bit about data movement and the cost that is related to moving data, and we mentioned that we need to optimize on the data movement. So sometimes the data that you want to move and you want to move in a single operation, it doesn't reside in either locally or remotely in a contiguous place, and you want to be able to take these contiguous places and make a contiguous virtual memory out of them. So I give you two examples. I think that the second example will be more of the common case, but first example is looking at 3 regions that are located in virtual memory, but they're not contiguous. They're in different sizes and different locations. But the idea here is that you could build virtual address space in the networking adapter domain that will consolidate those areas from V0, V1, V2. They'll consolidate them into a single contiguous space. And once it's a single virtually contiguous, then you don't need to do any conversion or any pre-copy in the communication library. You could just program that into the hardware, and this programmability is a very lightweight operation, and it's way more scalable than relying on a scatter-gather list. It's a more powerful mechanism, and you can do this, and you can avoid extra intermediate copies when moving the data. Another common example is looking at elements in a matrix, looking at what does it mean to extract a vector in a matrix, and instead of doing all the data type conversions by doing extensive data copy, you could avoid that and focus on touching the memory only once, and having programmed the hardware to look at those vectors as discontiguous data types, but with some kind of a repetition and a strided operation, and have the hardware just go and access each element from the hardware directly and save the data movements from the CPU. And this can definitely be used on transmit and on receive, and we think it's going to be very useful to save those data manipulation. Another thing, there's a big pain point around the need to pin memory for communication, especially when you deal with RDMA technologies. So, for communication, currently with the existing APIs and implementation, you have to pin down the memory. So every time you want to create a transferable memory through the network from user mode, you'll have to pin it down to register that explicitly. So it's not about only pinning, it's also about telling the adapters that this memory is accessible to the adapter. And once you do it, then you could move the data from and to those memories that are mapped to user mode. But the thing is that this registration and pinning just give some overhead. First of all, because it's an expensive operation, then there are many implementations that are implementing registration cache to avoid the overhead of needing to map that again. And also, once you start running into a memory pressure in the machine, you need to start releasing data and so on. And aside from that, there are other potential issues around fork and other things like that. By the technology of on-demand paging, we basically let you create a virtual address space in the adapter per process that is actually parallel to the same address space virtually in the process address space. And actually, the mapping between those virtual pages into the actual physical pages, same thing that there is a translation table of the CPU, there is a translation table of the hardware, and we synchronize them to point to the same place, but without the need to pin them down. So basically, once you turn on this on-demand paging, you don't need to do any pinning anymore. And if the page is released and the hardware table is synchronized, and whenever the hardware needs a page, then and the mapping is missing, it will be handled the same thing as it's handled in the processor by issuing a page fault. That's all magically handled by the hardware and the driver. So assuming some kind of locality, this new mechanism really simplifies the need. You'll not need to register memory anymore. You can play with protection information on access rights for a region, but aside from that, you don't need to pin down any memory. So this is about on-demand paging that will let you avoid the pinning needs for memory that is used for communication. So looking a little bit at the landscape of computing, so we see constant change there, right? We got used to having only x86 CPUs from 1.5 vendors, and then the accelerators came in, and this is now where we are at. And we talked about that, and that there are newcomers to here that are open platforms and are becoming a very strong, will evolve to be a strong alternative to those other mainstream CPUs. So definitely we're talking about the Power CPU and the ARM CPU. They have different instruction set than the x86. They have different implementation, cache sizes, attributes, system management, all of that. They do run Linux, and they run the same software. They are 64-bit, so they can scale to memories that are needed, but they all have different attributes. They have different compute powers, and they have different implementations, and there are multiple vendors that will be supporting them. So one of the key things from networking standpoint is to be able to adjust the networking capabilities and networking performance and tuning to this different platform. So we already saw that once we have those accelerators that reside on the PCI bus, we can come up with interesting technologies to boost their performance and to move data more efficiently to compute elements here. So we're going to see similarly on those open power and ARM CPU new technologies that will enable to move data more efficiently and to adjust the network capability, network performance point, networking price point to better match those new CPUs that are coming to play. And it's really important to have the best support. In terms of as you go up, it will preserve the same APIs, but you should be aware that some application will need more tuning to the different architecture, to the different number of cores, performance, scalability, and all of that. So that's going to require a lot of work from everybody around the ecosystem of those CPUs. So one technology that we mentioned, and we talked about that, there are a few presentations that covers that very well. I just reiterate on the evolution of the new needs that came in as the accelerator were introduced. So the efficiency originally of being able to move data from GPU to GPU to continue computation was very inefficient. So originally, GPU had to copy from GPU memory into CPU memory, and then you had to copy that by the CPU by doing a mem copy into a buffer that goes to the networking, and only then the InfiniBand adapter could access that data and so on the other side, so that was very inefficient. So this is where we came originally with GPU Direct 1.0, and that really saved that copy that was needed to done in the software here. And the next generation with the GPU Direct RDMA, you can actually move data from GPU into GPU. And all those innovations are, the very base things. And, we had a good talk yesterday about the remote CUDA that, enables you to share GPUs. And we talk about hybrid implementation of making sure that the data moves as fast as possible into and from the GPU. So all of these are, technologies that are very important in order to get the best efficiency from the new accelerators that come in. And definitely there are more and more things that can evolve in this area. So if you're looking forward into the new CPUs, and I kind of left this slide pretty open because it is, so I didn't write all of that, but we're going to see the CPUs and the networking in so many flavors. And they have to work well together, but they could come in different forms. So one of the questions that comes in mind many times is, will they be discrete components or will be integrated devices? And the actual answer is yes, because there is room for both of them. Each one has its own benefits. So I'll try just to highlight on the few things that could be interesting here. So if you look at the discrete world, we already are hearing about, the PCI Express that everybody knows here, but we've been talking about extensions or new alternatives that, preserve some semantics of PCI Express to some extent, but give some more goodies. So things like CAPI on the power world, and NVLink, that was presented by NVIDIA to better get more and more, bandwidth and performance. So this can give, discrete components, discrete integration, more benefits. And, another reason for doing discrete solutions is that we're talking about two different technologies that have their own evolution cycles. I mean, CPUs have their own multi-vendor, multi-stages of evolution. So they typically have, can have a TikTok approach of 1 or 2 years. So 2 years for every new architecture and 1 year for every improvement of process. Networking can work on different scale of getting, SDR, DDR, QDR. So if you want to make sure that you have the best in breed from CPU and from networking, then sometimes it makes a lot of sense to have them as discrete solutions. So this is why we're going to have discrete. On the integrated side, yes, we're going to see also integrated solution, and as a matter of fact, many ARM SoCs are coming with networking. But if you look at what this networking can do, then this is a very basic networking, minimal offloads and minimal scalability. It's just to be able to get in and out for very specific applications. And usually there is a big trade-off when you design a part that is a CPU, and you usually prefer to invest all the real estate on the die of the CPU to put more compute engines, more caches, and more things that will get your computation well. And then there is this NIC that you want to place into the CPU, so you have to do a lot of compromise in order to accommodate that NIC. So sometimes, and pretty often, you will be using a degenerated NIC with limited capabilities, for this case on the integrated device. So on the other hand, integration can reduce the power consumption and can also potentially bring lower latency if you invest a lot in, put enough silicon, so might be able to get some lower latency, maybe a cheaper cost, and maybe slightly cheaper, slightly lower power. So there are benefits here and there. So this is why we believe you're going to see both integrated and discrete. Same thing like today in the servers, you have server adapters and you have the onboard adapters. So people choose what to use. Usually for HPC, you'll need to make sure that you have the fastest and more feature-rich networking as possible when you build the cluster. So storage, we had a few good talks about the storage, so I'm not going to dive into many things in the storage, but with the current trends of SSDs and machines that have many storage elements, as well as distributed storage, definitely having a good interconnect is a key element here to succeed. With all the offloads that are in the hardware, with the ability to do fast RDMA that gives you zero copy, gives you all the transport offload, it makes a lot of sense to use that for storage, and we actually are seeing it. So I'm not going to dive into many details, but I can show you here, for example, is amount of IOPS that could be driven by regular TCP, or just go with ICER that is using RDMA, and definitely the performance is significantly better, as well as if you look at what's the CPU demand for getting those IOPS, then definitely if you move from non-offloaded to offloaded, you significantly cut down on CPU. So with different trends that we're going to see in storage and getting things to be more distributed, using storage maybe on every compute element, SSDs, all of those technology really can benefit from good interconnect. They can benefit from the RDMA, from the offloads, and they can benefit from quality of service, from high bandwidth, and actually the presentation that we saw in the last few days really showed the benefits that can actually be utilized by storage systems even today. I did want to mention something about data protection, because I mentioned all those failures that can happen, and one of the technologies that is used for data protection is called T10DIF, and basically the idea is that over every single storage block you can calculate a CRC, and you can add some running number, which is called a reference tag, that could that when the time you write the data and when you read the data, you can validate those things. You can validate that the CRC is okay, which that the data, nothing bad happened to the data. And when you read the ref tag, you can see that the logical block address is the same. So every time if something goes wrong, if the data integrity got broken, sometimes you can just read garbage data and continue your computation, your work with the garbage data. So there is enormous pain of recovering that afterwards. So ideally, you want to isolate the errors as they appear, as they happen, and you want to take the actions when it happens. So this is one of the technologies that really enables you to do that. So we see this technology both in block storage, and even you can look at Hadoop file systems and other places. Being able to calculate some kind of a signature in the block will let you identify the errors as they happen, and take the action when it's happening. And errors are going to happen because of software errors and because of hardware errors, especially at this large scale, and you want to take immediate action once something goes wrong. So the idea is, calculation of CRC and all of that, and insertion of those interspersed data and this metadata of few bytes, those things that requires a lot of processing in the CPU. And part of the features that we added in Connect IB is to offload the data protection calculation. So basically, as the data flies through the wire, for example, in this case, you can have an initiator that even doesn't have this protection information. And when the data flies in the hardware, the hardware could add the calculation and plant those metadata into it. And also when the data comes in, and as a result of IO read, the hardware can strip this metadata and validate that. So every time something wrong happens with the data, you can isolate and identify this as early as possible, and then you can implement the action, and you avoid the propagating error into the system. Okay, power is very concerning thing, and we've seen in those presentations of DigiPanda that we're close to the envelope. And one of the key things in power is yes, we need to save power, and we need to do a very efficient power design. But what I wanted to talk more here is the difference between the peak power that you consume into the actual power that you're actually consuming, because you do have to design the system and the cooling and everything to the peak power that will be consumed. Maybe the single task that will be very computation and network intensive, but actually when you run jobs on the cluster, it's going to take way less demand from the compute, from the network, and so on. So as a company, we participated in an European Commission FP7 program that's called ECONET, and part of the concern there was that devices that operate today, their power demand is not proportional to the actual service demand. So basically, if you move data or don't move data, they take the same amount of power, and that's problematic design, because everybody knows that the hardware is not 100% utilized all the time. Even though we make a lot of effort to utilize that, still you have job schedulers, places where you can't optimize for 100% utilization, and you place multiple jobs that don't communicate between themselves. So all of these lead to the fact that you don't need the hardware 100% of the time, all the hardware. So basically, and power costs money, and definitely this is OpEx that you would like to save, both on actual power of the hardware as well as cooling expenses and all of that. So we went again and looked at the different components in the system where you can optimize on power demand and power consumption, and we realized that it's all over, right? You have the link level where you can save power on the link itself. You could reduce the width. So today the typical width is by 4. It's a by 4. It's on the PCI Express. It's on the PCI Express. It's actually by 8 or by 16. On the SerDes, it's a by 4. And when you're light on traffic, you don't need to utilize all this by 4. You can power off lanes and reduce the demand, the power demand. You can look at technologies like energy efficient Ethernet. You can do on the ASIC level voltage and frequency scaling. You can shut down arrays. You could turn off completely ports by management. So if you understand the topology and understand the scheduling and understand the jobs, then you can power off parts of the system. And actually powering off brings you the best power saving possible. And one interesting thing is that even if you pay attention to the fan control, you can also save some power there. So those are a few examples of speed reduction going down from FDR to SDR. You can see that you could pretty much save from 100% power demand into about 65% if you go down in speed, and actually even more. Substantial saving in width reduction. If you go down from 4x QDR into 1x QDR, you can save about 57% of the power consumption. So those are just examples, and the idea is that you can do that dynamically. So if you look at width reduction and speed reduction, then what you can basically do is you see that there is no traffic, then you reduce the width, and if it's light traffic, that's fine. If you see that things start to pile up, then you would take the link back to full speed. And actually, those are policies that you can play with, and if you're very conservative and care only about the performance, then sure, you don't need to turn on power saving. But if you do care about power saving, you can turn on certain heuristics and take advantage of this. Some other things you can see is looking at power consumption by a switch with the width reduction and without it. Definitely depending on the load of the switch. If the switch is 100% loaded with traffic, then yes, you need all the power. But again, the lower you get in terms of bandwidth per port, at some points, we can start doing width reduction, especially when you have light traffic, and then go from 85% down into 60%, and all this power saving will be substantial. Another thing is, closing ports, and you can see again, if you don't need all the ports, you can try to shut them down. This is something that could be done by management application. Once you shut down the ports, you can really save on power, and you can even shut down complete systems, especially if you're dealing with topologies like FAT-tree. It's pretty much straightforward to turn off spine devices in the network if you don't need them. And this could be, a management integration between, job scheduler and subnet manager and all of that. You can even do it almost painlessly without losing traffic if you do it right. So those are things that can really improve the power consumption. And last thing is about the fan systems. It's funny, but the fan, the fan when you turn it fast, it takes a lot of power. So basically this one shows the temperature of the switch. So once you try to cool down the switch, you start investing in, if you go left on this graph, you turn the fan really fast in order to put the switch into a very low temperature. So, the contribution here to the power is actually the fan that goes really fast. And once the fan works slowlier, then it consumes less power, but then at some point the switch temperature starts to go up, and once the temperature of the switch goes up, it takes more power. So you do need to find the sweet spot, and actually one curve per each load on the switch, so it's more challenging to find a fan algorithm that will also tune and optimize the power demand of the switch according to the actual load and the traffic patterns on the switch. A few words about monitoring diagnostics. This is also something that is very important, especially when you scale. And you probably want to visualize it. Some of us don't like visualization. They can, run the diagnostic tools from command line and do their greps and set an awk, but some people just like to see it visualized. So we have one example is the Unified Fabric Manager, also called UFM. You can look at the topology there, do some health monitoring, get insight into congestion analysis, get alerts and all of that. So that should be make the life easier to manage the networking of the cluster. And last thing that I just want to highlight, and we don't know yet, whether cloud will adopt the whether HPC will adopt all the cloud concepts. But there is some interest to see different cloud and different big data technologies. And we basically are seeing ability into clouded environment to bring goodies of bare metal performance. So technologies like SRIOV that can let you kind of slice the device and give a function to a virtual machine. Those technology can really let you leverage virtualized technologies, virtualization technologies, as well as getting optimal performance. So we're doing some reference design for cloud running on commodity hardware with optimized networks, because what we do see is that some of the clouds are not fully optimized for performance, especially not on networking. They might be more service rich, but getting the best performance from networking is a critical ingredient. We have here some reference architecture for the cloud, running all open source component with hypervisor of KVM, OpenStack, and all of that, and optimizing the networking by running SRIOV and optimizing the storage with SSD and high spindles count. And basically, we're seeing significant improvements in all those technologies that are also used for big data. So now you can use them not only on bare metal machines, but also on virtualized environment, and still, get significant, performance improvements compared to other clouds that don't focus in optimizing the network. So basically, we see a lot of value in having best-in-breed networking to optimize those clouded environment and big data environments. So that's pretty much it. So I hope I give you a lot of high-level ideas of things that we're doing and we will be doing, and we have interesting trends and a lot of work in front of all of us to get to exascale. Thank you.